Whoops. How do you like that? Pretty nice, huh? I made this picture actually. Well, I didn't make it, but I modified this picture uh, to make it look this way. The original was similar, but it was more like olive fog, and I made this part a lot clearer than it was originally, so that it looks like a camera focus. Anyway, back to my struggle with the unsolvable, seemingly unsolvable mirror mystery, and how this follows, which I'm sure it's not the only time that argument was used. Well, maybe it was the first time. There's some mention of, yes, I even put it, highlighted it. Superposition, a process by which one magnitude may be conceived to be placed upon another so as exactly to cover it, or so that every part of each shall exactly coincide. Okay? Now that is essentially the definition of A equals B. If you want to say that A equals B, you can use this superposition. What does this say? Okay, vertically opposite red and yellow. When the legs of an angle are produced or prolonged beyond its vertex, the angles made by them on both sides of the vertex are said to be vertically. Oh, no, it can't be. Hang on, this is referring to this picture. And I haven't really read this that closely, but I didn't think there would be much to learn anything. Right. When the legs of an angle, I should know what legs means by now. That's the bottom part. Where did it say what a leg is? Oh, here we go. The vertex is the point where the sides or the legs meet at A. When the legs of an angle are produced or prolonged beyond its vertex, so that means to continue onwards, the angles made by them on both sides of the vertex. Okay, well, which side is down and up? In this case, it would appear the side being defined by the vertex and the line. So this G and D here are on opposite sides of the vertex in the red direction. The angles made by them on both sides of the vertex are said to be vertexally opposite. That would say to me that this is vertically opposite this, but that's not an example. Thus, the red and yellow angles are vertically opposite. Oh, these ones. Solid red, solid yellow. There are two yellows. Oh, wait a minute. Now they're confused. Why choose red and yellow? Why not choose blue and blue? At least thus, Thus, the red and yellow angles, red, yellow, well, they seem to be vertically opposite for vertex C, but they're not produced beyond, prolonged beyond, legs, prolonged, red angle. Red angles made by these two legs, and they are prolonged. So therefore, I would say that if I were to read that, these are vertically opposite, not the other ones, even though vertical usually means up and down. I suppose it's possible that the word vertical, actually derives from vertex. So they're opposite vertex, opposite sides of the vertex, right? So vertical doesn't mean this, it means vertex. Huh. Well, anyway, that shouldn't matter. I continued thinking about that proposition, and or the proposition that all these any propositions wherein a comparison with a mirror image triangle is taken, and I believe that actually Euclid is simply taking these as being trivially different. That is, he hasn't realized that he's making an assumption here that isn't, well, it follows from the axioms, it turns out, I think, if my proof is correct, but it needs to be shown that two figures that are similar to, at least two triangular figures that are similar in the sense of all their sides being equal, are also similar in their angles, and I think he's just taking that as a given. But it actually can be proved from the axioms. Similar triangles is also defined somewhere. Now, I don't understand this axiom, or exactly fill the same space. Okay, magnitudes. Alright, but that's not shapes. That's not the same as saying a triangle. One triangle is not equal to another triangle if their areas are the same. They just have the same magnitude area. Somewhere in here, there's a mention of similar, something about things being similar. But I don't see it. And in any case, it needn't be said, because I believe it follows from the axioms, that two triangles having all the magnitudes of their sides all equal, as in this case, this triangle and this triangle are equal in their corresponding angles are equal. You have to find that. It's not right. Oh yes, there was something I wanted to say before that. just to like throw something into the mix, I guess. To confuse, if you like. Something I worked out just as I was fiddling around. Now, I'm going to define, go back to Descartes' world, and I want a brownish color, and I want this to be 10 though. Now, 10-degree angle, 120, how big is that? A little bit bigger, maybe 180, bigger. It should be 200 actually, almost 200. Okay, good enough. I'm going to call this first. This is the x-axis, as you all learned in school, high school, the Cartesian axes, x and y. Now it's possible to invent a different set of coordinate axes, as I have here. This one I'm going to call the u-axis. Get that color code. And now the other axis I'm going to draw, the other u and they're going to be u and v. This doesn't need to be 200. This needs to be about 150. That's 400. 200 gave me. See, this is 2 now. Can I do it with ones? 200? No. 100, that's 100. If that's 400, and that would be a little bit more than 100. Let's say 125. Close enough. And this here I'm going to call the v-axis. Alright? And I'm going to, just in a familiar way, whoops, you're used to from high school, draw a point, maybe even show its coordinates in the plane. Now the white here indicating the y, the x and y coordinates of this point, which I could label P if I wanted to. Okay. Now, if I were to imagine u and v as another set of coordinate axes that somebody might be using for their measurements for whatever reason, it's a restriction, then the way one would do that, unambiguously and consistently, with the parallel postulate and everything, would to be in fact, why don't I make this a slightly different color? Then I can show it more easily. Something like here. Oh, I gave it the wrong colors. This one's the wrong color. They're both the wrong colors. This one should be the darker brown. This is what I have. Which I could also draw up here. Fit. It's a little bit too far, see? So what I can do is fix that before proceeding. I'll keep this here. V. Now these arrows are just fictions that I've made up in order to prove a point that one can arrive at the point P completely in a completely unambiguous way using a number line system like these ticks along U and along V, right? And assign two numbers, U and V, to a point that wouldn't be the same numbers as X and Y. Okay? Now, 2 points in this UV land would be, 2 lines, I should say, would be parallel. For instance, these two would be considered parallel lines, right? Because if you extended them forever using the system that I just told you, they would never meet. They would be parallel in the Euclidean sense. What about something like this point? Suppose we had 2 points like this. Well, actually, I don't really need the second point. Suppose I have a point and I want to draw a line parallel to this line. Can I do that unambiguously? The answer is yes. I would make a line. Oh yeah, I changed my key binding. This unbounded. Maybe like that. That's not exactly right. Well, I copy this one. Put it there. Now there would be no other. I don't think that I can find another. And I want that point here. Do I have clear points? How did I just want one point. In UV land, they can't see these are coordinates or these numbers, so I can turn them off. Given a point and a line, which I've taken, I can draw a point. I can draw only one line parallel in the UV sense to that line. But what about a line that's not parallel to the axes? I mean, does it follow in that case? Okay, suppose we drew a line. I'm going to draw a line in any color somewhere. Right. In UV land, I draw another point, another white one. Here, and I want to draw a line that is in my world parallel to this line. Now the question is, first of all, is this a straight line in my world? And the answer to that, let's see, I believe is yes, because the increase in this amount appears to be proportional to increases in this amount. Okay, it would be viewed as a straight line, definitely, in that world. To prove it with 100% certainty, I could make a formula that would tell me what u is as a function of v on this line, because I know its formula in this coordinate system, and I can transform it. And it turns out that I already worked it out. The transformation formula involves sines and cosines, a mixture of them. It's similar to a rotation formula, but with a sign difference. And I'm trying to think if I've plugged in that into an equation for a line, do I get a UV line? I think I do. The U's and the V's, I'm wasting too much time on this, but it's something like this. X, cos, some angle, V, something like that. VHR. And V is similar, but the cosines and sines are reversed. And the signs are the same, and there might be a scaling factor. Now, the equation of this line in x and y is, let's say 3x, something like that, plus 7. Whoops, this is v. 3x plus 7, plug that in for x. And for y. So the relation between u and v would be a linear one, definitely, right? Because this would just be some scaling factor times x, and this would be another scaling factor times x. And moving along this thing in a uniform fashion is the same as increasing x in a uniform fashion, right? The relationship between u and x is like this, linear, right? V is a fixed number, the relationship between u and x is a linear one, and same with y. It's a line. So if y is linearly related to x, then u will be linearly related to y. This is what linear algebra is about. Linear relations. Okay, so I can say definitely that this would appear in the UV system as a straight line. Not sure what it would look like, what its slope would be. I'd have to work it out. Alright, I just want to draw one more thing. This here I just added to my thing. Now, I don't know. I did 10 degrees there. Okay. 0. Yeah. Color. This shape is let's see, that's with the positive one. Right? This is how in the UV system a perfect circle in the XY system would appear. So if I drew a perfect circle of a radius 100, okay, in my land, and then viewed that in the UV land, you can actually see that it certainly gets fatter as far as UV is concerned. this is looking straight up, and at angles below the axis, halfway between, in the third quadrant, my regular old circle would appear to be a great distance away, more u and more v, than if I were looking at it at a 45-degree tilt in the UV land. So this does look like the correct how it would be viewed in the UV land. Well, it turns out that this shape is exactly an ellipse. And I don't know what radius it is. It's not 100, I'm pretty sure. It might be near 100. I don't know, let's just try. I have to rotate this ellipse the wrong way. That's differently, it looks like it's bigger. Less skewed. Okay, that's way too big. Maybe 120. Closer. Getting there. There, almost. You see how close that is? That's not a coincidence. In fact, the formula turns out to be exactly an ellipse. Now, this I think goes down a bit. Whoops, too far. Maybe I was off the other. It's very close to get it right. There we go. It's almost exactly it. Why don't I make it a different color? Okay, now if you fiddle around and if you had more decimal points, you can fit that exactly on top of this. It's an ellipse. A circle in UV land, my circle, sorry, my XY circle in UV land becomes an ellipse. Okay, so that's why one ought to be careful about things like, reflections and stuff like that, and whether or not things might change. The shape of something, what appears to be rigid, may depend on what region you're in UV land. Right? UV land is not exactly Euclidean land. For instance, the distance formula would have to be altered in UV land to something else if you wanted it to be actual distance, in the sense that it doesn't change under things like moving things from one place to another, or rotation, and so on. Alright, enough of that. So I wanted to show that similar triangles. I've used too much time. Maybe I should stop there. I've called it Allen's Lemma. I'll read it out and then I'll prove it next time. So just go through the lemma, and you can think about it too. It'll take long enough just to read it. So here's Al's lemma. And then I noted this. It might be that this lemma is in the original book of Euclid, something similar, but was left out of that particular abridged version, perhaps. Two triangles, all sides equal, are similar in that the angles of corresponding vertices on either triangle are also identical. Okay, that's what I want to prove. So that would allow us to make those comparisons, the similarity between triangles with mirrored vertices, vertices, I guess, mirrored vertices versus the other direction are the same in every respect, and that the mirroring has no effect on any of the main properties of the triangle, that is, lengths and angles. Now, so first, I haven't mentioned mirrors. I said the result follows trivially when the triangles correspond exactly. This is an exact correspondence. Assuming same color means equal sides, right? These triangles are trivially equal because I can obtain this one by simply rotating this one around until the reds, say, coincide, and then the other lines will coincide. It follows by that theorem. We match up one base, and we have two sides coterminal on a base, on some base, and it wasn't coterminal. Conterminous. If we let's say we use red as the base, and went to that theorem 4. Where is theorem 4? This one here, and these here being the equal other sides, which are equal and coterminous at either end of the base. That would be the case in this case, because these would be on the same side, and so would the whites. So the result follows trivially in this case. Okay, that they just are simply rotations away. Where the second triangle is obtained from the first by simple rotation. In such cases, we rotate one or the other until one of their equal sides coincide, and deduce that the remaining sides must also be coincident by supposition and theorem 4. Okay, I'm glad that I didn't forget. We still need theorem 4. Alright, now what I've done here is label the sides with the colors of labeling the letters. It's hard to tell between B and C, but B is a bluish color. I can select it this way. Make it more blue. How about that? It's more ugly, isn't it? Okay, I'm calling them A, B, C, with the color of the letter indicating which side it corresponds with. I don't know if I can't get that one. Alright. Now, so as far as the rotations go, like the example I just showed you, if we take the ABC letters in a clockwise way, we could describe these triangles, for instance, here as CAB if we wanted, right? Then this one would be blue BCA, and these are rotations. These correspond to rotations of the same object. There are three possible ways of labeling, the size through rotating, and there is one remaining one which isn't indicated as a picture, but that would be the one that has the red on the bottom. I'm putting the bottom, reading off the bottom, one first. It doesn't matter how you look at it. Labels are arbitrary. You can read it however you like. However, these combinations don't correspond to any of these ones, and they can't be obtained through rotation because these correspond to the mirror image, which is this triangle. Okay, that's the mirror image triangle of this. See? If I bring this up here and put a mirror here, this is the mirror image of this one. Okay. The corresponding angles are defined, so I'm defining what I mean by corresponding angle as those with those angles whose vertices contain two equal sides. So this angle corresponds with this angle in this picture because this has a blue and a white side. And this angle, blue and red, corresponds to this angle. So the correspondence is same color. So, and I've indicated all the corresponding sides. They have the same letters, right? So BC and CB, or AB and BA. Now I want to show that those angles are exactly equal in their magnitude as the ones in this triangle, and that is something I think I have proved on the next page, which I don't have time for, but I'll do it next time. Okay, see ya.